Okay, cool. You can start out.
All right, so I'm giving a presentation today on Pandas data frame and also local operators. So first we'll start. What is a Pandas data frame? It's basically like kind of think of a table. So it's a two-dimensional, size mutable, and potentially heterogeneous tabular data structure with like labeled axes, rows, and columns. It's pretty similar to like an Excel spreadsheet or like Google Sheets or an SQL table, and it's incredibly used in Pandas. So why are they important? So they offer like a lot of advantages. So first, data frames are two-dimensional and table-like, so that's really useful because essentially you can have like the columns represent different fields and the rows represent different like records or like different like items or objects or whatnot. There's a very efficient data handling. So basically, they're very efficient with like storage and manipulation of data sets. There's like indexing. Also, like another strong suit of them is they use NumPy, and NumPy is incredibly efficient, incredibly fast. It speeds up a lot of like matrix math and like that sort of thing. Data. So another advantage is data analysis and processing. So there's a lot of operations for data analysis, such as grouping, pivoting, and summarizing. We'll look at some of those later on. And compatibility, it can integrate well with other data analysis and visualization libraries. So how can they be used? They can be used to clean data. So let's say you have two different fields and you have like a bunch of like records and like bunch of like items in that like in this table. You can essentially let go of like any items that might be missing values or anything like that, or you might only want, let's say you have a group of people, like you have a data frame of people, you only want people who are above like 5'4" so you can filter through that. You can also change data types, which is really useful. So data transformation, so you can also like add, delete, modify columns. You can merge data sets. Data analysis, there's a lot of like statistical analysis, especially some like descriptive stats, some aggregations and summarizations. They're very easy to visualize with libraries such as like matplotlib or Seaborn, and machine learning. So data frames are very useful when it comes to like machine learning for specifically for the purpose of pre-processing, which is something that like the Cylon project is like focused on. So what are some unique features? There's advanced indexing options. So you have like hierarchical indexing. There's diverse data types, so you can basically store like a lot of different data types. Like for example, numeric, string, date time. There's missing data handling, so there's like it's really easy to check for like records that are missing table. It's easy to check for like items that are like missing fields or anything like that. Time series functionality, so there's you can do a lot of like analysis on like things over time. And there's like really easy, it's super easy to like import or export in different formats like SQL, Excel, JSON, whatnot. Here's some dependencies. So the biggest dependency is NumPy. This is what like helps pandas do a lot of like the math operations, a lot of like the matrix multiplication, like I said earlier. Python date util and PyTZ is what handles like the date time, like we were talking about that data type earlier. And there's a lot of different like optional dependencies that you can use that you can like integrate really easily with pandas, like matplotlib, SciPy, and SQL Alchemy. And like there's many more. Like you can just like look it up. There's like probably hundreds. Okay, so let's talk a little bit about local operators. So first we'll start with dot join. So basically dot join lets you combine two or more data frames based on their indices or a key column. So for
Hey,
example, let's say,
Arup, sorry to pause you. Could you please explain what do you mean by local operator?
oh, so basically this is a type of operator that happens like a local operator is kind of just like on like the local machine, like it's kind of just like happening like within one machine. It's not like you're not going through like different like data frames on different computers. It's basically just all on one machine where it's like a distributive. Well, I'm pretty sure that's how it works. If you can correct me if I'm wrong, but like
Yeah,
a
yeah,
distributive.
you are right. I know what is local operator. I just asked this question to
Again, yeah.
basically let everyone know they might have these questions. And if you guys have any question, please feel free to ask Arup. He will explain or probably I can jump into. Okay, continue please.
Yeah, so this puts it like essentially combines like data frames together. So that's really useful. Like, hey, let's yeah, like that's the main usage of join. And sort values. This is also very useful. Basically, what you can do is you just like put in like you put in like what type of like field, like what type of column you want to sort by, and essentially what it'll do is it will just do like a very like quick, like it will quickly sort the table, and you can like see like basically like what the different data types, or like you can see like how the table changes. um and then there's also group by, which you can like group data by like one or two or more columns and perform like a bunch of operations on that. So like let's say we want to like look at like different like we can like look at like all the different types of animals. Like basically it's like here's an example. It's like let's say we have like two falcons and two parrots. Basically what the group by will do, it'll put the falcons together and it'll look and calculate the mean of that. And then it'll take all the parrots together and it'll calculate the mean of that. And then it'll like return that in a new data frame essentially. There's also merge, which combines data frames based on common columns. So basically it's like so like also okay, I'll explain this. So there's like different types of merging. So there's inner join, which is basically like you'll only join records or fields that are basically exactly this, or that have like, or not exactly the same, but like are same based on like your like parameters. But then there's left join, which will basically, let's say you have two tables, a left table and a right table. Basically, for your if you're left joining, then it'll look up, see what matches on the right table, and it'll add that to the left table. Whereas right will do the opposite. So like it'll take the right table and it'll see whatever matches with the left table and put the matches into the right table, and then the outer table just like adds like everything essentially, like if there's matches. And so yeah, like this is like a super like useful this is also a very useful operation. And then I think that I thought, okay, so that's like the last one I have here. And then I also like did like a little like fun little like made a fun little like project where I can like show off like why data frames are really useful in terms of like analyzing data and stuff like that. So here, let me just change my screen. Um, so yeah, so what I did was I essentially like took data from Kaggle that like gave off like the shot charts of like LeBron James, Steph Curry, and James Harden, which are three NBA players in like the 2022 to 2023 like NBA season. So let's just skip over here. So basically, like as we can see, like let's first like import. The first thing we're gonna want to do is import the data and like just get like a little summary about it, like understand what's going on, like what's the like the structure of the data frame and stuff like that. So it's super easy to like import. So first we're gonna want to import both pandas and NumPy. That's like the most important thing that we do. And then all like there's so many different like for pandas, there's so many different helper functions like dot read CSO. Oops. There's like dot read CSV. There's like probably there's like dot read Excel files. There's definitely like you might have to use SQL Alchemy for this, but like you can definitely like get data from SQL. Like there's so many different ways to import data, which is what I was talking about earlier with the like easy import export. And then another feature, a function that we use here is dot head. So basically use
Hey,
dot
or
head.
could you please hold a bit? Could you please comment out that import NumPy line
Like commented out
and only import NumPy one, not the.
like
Can
this.
you run it again?
How do I run it on this?
Control Enter. Are you at the notebook or something?
Yeah, it's like
Yeah,
the online version.
yeah, it
Oh,
is.
oh,
It
it's
is
still
running. So that means we don't need NumPy for this, but probably NumPy will be used later. Yeah.
yeah. So
Anyway, yeah, go ahead. So
so as you can see, like it gave like a summary on like, oh, here's LeBron James. He like basically what like top left does is this, it's like how like high up the shot is, like, and how, and then like from like the bottom of the basketball court, or not the basketball court, but like the half court, like from the bottom to the top, like how far up is it, versus left is like how like far to the left is it from like the right, very right, essentially. So it's basically like a coordinate plane. And then you can see like there's a date, they give like quarters, like how long was left in the shot clock before he shot it, or not the shot clock, but like the game clock. Um, like if the result is basically false or true based on whether he made it, the shot type is like, was it a 3 or a 2? And like there's like other stats like this, and you can see we have the same thing for James Harden and same thing for Steph Curry. So here we can like figure out more info on like the structure of the data frame using using a function called .info. So for example, we have like, we run .info on like the LeBron James data frame, and we can see like there's like top, like there's basically it'll tell you the column, and it'll tell you the column number essentially, and it'll be like, so what type of object it, what type of data type it is. So like top and left are both like just 64-bit ints. Date, quarter, and time remaining are all objects. A result is a boolean, and you can also see the count. So basically it tells you how many like valid like data points are there. So basically, like you can see, this is a completely filled out data sets because everything has like this a very consistent like 1,533 non-null entries, which is the same amount of entries as the whole data frame as a whole. So that's really great. And then it actually tells you like the memory usage and stuff like that too. So like that's really useful for like storing it, because like, I mean, like even if you're using like a cloud system, but specifically because this is like more of a local project, you only have so much memory on a computer. So it's always good to like know like how much like different storages different data frames take. And then so descriptive statistics. So basically another very useful thing we can do with the pandas is literally just like figure out what like some like just some plain stats that you can like very quickly like tell a story about. All right. So here we can do like, oh, so there's like, it tells you like the counts. If you do like describe, it'll tell you, oh, here's the count. Like there's this many entries, like we got earlier with .info, but it'll also tell you what's the mean distance. So like this is like really useful, right? Because let's say we compare LeBron James to James Harden, right? LeBron James takes shots that are that are on average like much closer to the basket than James Harden does, and even and Steph Curry takes like the farthest away from the basket shots in terms of like just distance from like the baseline. Whereas they both like, everyone like relatively has like relatively similar lefts, except so it's also like interesting because like it just tells you a lot of different like things, a lot of just different like basic statistical information that's like really useful, like standard deviation, the minimum, the maxes, like, and like the quartile, like the interquartile ranges and stuff like that. So that's really useful. And then okay, so like let's say we want to like really like we want to figure something out. So there's a statistic in basketball called effective field goal percentage, which is basically a way of like taking into, it takes in your like field goal percentage while looking into your while counting 3-pointers as like being more efficient, because 3 points is more than 2 points, right? So basically what the formula is, it's like you take the number of field goals plus half of the number of 3-pointers, and you divide it by the field goals attempted. So that's just like how the statistic works. So let's try to figure that out. So there's a lot of really like interesting things you can do. So like you can be like, one thing we could do is we could be like, let's just say we could use dot value counts to figure out how many times a value occurs within a specific data frame and for that specific field. So for example, we do LeBron James, and we're gonna actually like index. You can, which is something that's really good about pandas, is you can index into the column. So we're gonna index into the results column, and we're gonna say, hey, look, here's the value counts, and let's print this out. Let's figure out what it is. So LeBron James has made 768 shots last season, while he's missed 765. So then we learned like also like it tells out the data type and stuff like that. But then let's just figure out like let's figure out if we can use the dot get method to figure out which shots were actually made with true, right? So we can just I mean like yes we can see that, but if we specifically only we can already see that with value counts, but if we wanted to like be even more specific, we could do dot get true, and we see that's 768, and then okay, so now next we need to figure out how many 3-pointers he made, right? So we're gonna do made shots. So we're gonna filter so that you can like filter through data frames by doing like doing the data frame, then like going to like choosing the column, and then like choose is like equal to true or equal to false, or is greater than a certain value, less than a certain value, equal to a certain value. Like there's so many like basically any sort of conditional you can index into a conditional essentially, and then you'll return a data frame with only the values that like fulfill that conditional. And then here we like you call dot head on this new data frame to like figure out like what just like I don't know, show some like summary data. And then we're gonna do the same thing when we're gonna do and we're gonna look at the made shots he made, right? And then we're gonna take the shot type. So the shot type, remember it was either 2 or 3 for 2 points or 3 points. And we're just gonna dot get 3 and see like how many shots he made. And yeah, so basically if we scroll down here, we see he made 152 3-pointers. So and honestly, for this, and the last point, so right now we have the number of field goals made, the number of 3-pointers made, and all we're missing from the formula, as you remember, is just the field goals attempted. So there's a really easy way to figure this out. This entire database, the data set is basically all the shots he took, so all the shots he attempted. So if we literally just like call length of, which is another nice thing you can do, you can just simply call length or len parentheses data frame, and it literally will just return like how many records or how many like rows are within this data set or within this data frame. And now we just have to put that all together into like put together all 3 of these variables into a simple like formula. And then we have the effective field goal percentage of LeBron, which we was found to be 55 and like a half 55.1% essentially. But now let's try to do this, but all in one line. So this is kind of like, I wouldn't say normally this is like what you should do maybe, but like it is cool to see how you can just do, instead of doing these all one by one atomically, you can just essentially just have one line that literally just runs everything. And as long as you have all of your like, as long as you have all of your like parentheses, all your brackets, everything closed in the correct way, then it will always like it will be the same thing as doing everything one by one. So like for example, we see like this specific thing. Let's say what will it do first, right? So basically there's a division here, but there's this giant parentheses here. So first we'll like work in the parentheses, like do some PEMDAS. So then we'll do so what this does is it does James Harden's, it'll search through James Harden's, it'll see the results, it will like specifically get the value counts. So like it will return a data frame of like how many he made, how many he missed, and we're gonna specifically get the amount that he made, and then now we're gonna add that by half of the size of all of the shots that he made where the shot type was a 3, as you can see here, like we did earlier. And then once we add those two together, we're gonna divide by the length of the data frame to see all the shots that he attempted. And there's some like other cool things we can do. Like here's an example. We use the group by function that the operator that we talked about earlier, where we said, hey, let's look at let's just see like how distance from the field affects or let's see how likely, the average distance from the field. Let's look at how far like the average made shot is versus the average missed shot is. So here we can see like LeBron James's misses are usually much farther away than his makes. But however, on James Harden, like they're still pretty close. But then even Steph Curry makes more shots that are closer to the basket. So this is really interesting because we can like find out that oh, James Harden, it doesn't really matter where he shoots from. He's kind of equally efficient everywhere. He's relatively equally efficient everywhere, according to the like this small little data we have here. But then, so like we can see like all this like data and stuff. Like Pandas data frame is really useful for like basically just like telling a story about like very efficiently organizing data, very efficiently like fixing like any missing data. Like it's just a very great tool that has like really good integration with Python, and Python's already used for so many like machine learning or even just like different applications in general. Like for web development, we have Django. For machine learning, there's PyTorch, like and TensorFlow. So it just proves that like Pandas is like just incredibly important. The Pandas data frame and Pandas as a whole is an incredibly important library for any type of like for like any type of program. So I think that's everything I have. So if there's anything you want to add.
Thank you, Arup. Do you guys have any questions?
Yeah, I'll stop sharing.
Okay. Okay, the next is Shreya. Shreya, you can start your presentation.
Okay. Can you see my screen?
Yes, we are.
Okay. So basically, I'm just going to do an extension of the previous presentation, but this time, instead of focusing on the local operator scale, we're going to kind of extend it and go more into the distributed operator. So first, what is a distributed operation? Basically, the main idea is that distributed operations involve the parallel processing of data across multiple computing resources. So instead of relying on a single machine, tasks are essentially divided and executed on a cluster of interconnected machines, whereas a local operation is just one specific machine. And the benefit of this is that this approach enhances computational power, which basically allows users to handle large data sets and much more complicated operations very effectively. So to think about this in terms of like an analogy, for example, we can think if you have like a really big task to complete, like sorting a massive stack of papers, for example, and like if you try to sort the massive stack of papers like alphabetically by name all by yourself, it would take an extremely long time. And that's kind of like comparing it to the local operator. But if you get a group of friends to help you stack the papers together, like you each take a part of the stack and stack it independently, the work gets done much more faster and much more effectively, which is kind of what the distributed operations is doing. So the two main parts for distributed operations are data distribution and parallel processing. So for data distribution, large data sets are divided into smaller chunks, and each chunk is distributed to different nodes within a network. To recap what a node is, it's just basically an individual machine or computer within a network, and each node can work independently and perform tasks and execute operations. And then parallel processing is when these tasks or operations compute things simultaneously and independently. So if we go back to that analogy with stacking the papers, the data distribution can be compared to dividing the papers into multiple stacks. And then the parallel processing can be compared to like I don't know, like working together, like each friend working together to stack the papers at their own time, like their own time. So like each person's working simultaneously and independently. And like the combination of both of these increases the efficacy of computing whatever you want to compute. So just as a recap for the two things that were mentioned in the previous presentation, NumPy is just a library in Python for numerical and matrix operations, whereas Pandas is an open source data manipulation and analysis library for Python, and it provides data structures for storing large data sets. So the problem with these libraries that occurs when you're trying to use them for really large data sets is that the memory on your laptop or the machine can run out really quickly. So a way you can mitigate that just by using Pandas, for example, is There are 4 ways, one of which is loading less data. So like only loading the columns that you need to load. So for example, in a data sheet, if you have a column that just specifies the trials and you don't need to do any analysis on the trial number, you can just not load that column to help save memory. Another way you could scale Pandas to a larger data set is by using efficient data types. So you go through the different columns and see which ones take up the most space and see if you really need them in your analysis. So for example, if you look right here, the name category right here in this data sheet takes up a bunch more memory in comparison to the other labels. So a good way to kind of mitigate this memory issue is by transforming these high memory usage columns and converting them into categorical variables because they take up so much less memory. And then sometimes another strategy that's used to help scale analysis to larger data sets is chunking. And that basically is just splitting larger problems into smaller ones that can fit in memory. And it's not always used, but it's sometimes used. And the main topic that I'm going to be going into, which is used a lot more frequently, is Dask. So Dask is pretty much a parallel computing library in Python that's designed to enable parallel and distributed computing for really, really large data sets that can't be handled on a single machine alone. And the main purpose of this is to extend the capabilities of these libraries such as Pandas and NumPy that work really well on local operators, and then just scaling them to be really big so that you can move from performing these computations from a single machine to a cluster of multiple machines seamlessly. So many operations in the Dask data frame are intentionally designed to mimic these other libraries such as Pandas and NumPy, which is why I don't really talk a lot about the specific commands because they look very familiar. And the whole point of this is so that people who already have experience with working with Pandas and NumPy can transition very easily to working with Dask. So some key properties of Dask. First, it helps maintain parallel and distributed computing. So it allows the parallel execution of computations on a single machine, and it can also scale out to distributed computing environments, distributing tasks across a cluster of machines. So if you have a really big computation and we split up the tasks and put them across a cluster, the efficacy increases really well. And then another key property is lazy evaluation, which is basically something that Dask specifically uses, and it pretty much just builds up like a task graph that represents the computation instead of actually executing the computation. And what this does is that it allows for really good, efficient scheduling and the optimization of computations before you actually use up memory to execute them. Another property is distributed data frames. So the Dask data frame provides like a Panda-like interface for working with really large data sets that, again, can't be done on a single machine. And the operations on the Dask data frame trigger like the creation of the task graph, like I mentioned previously, and computations are just executed based on when they need to be executed. And then lastly, a really big important property of Dask is the scalability. So the whole point of Dask is to enable users that are used to working with libraries that are suited for single machines to scale them from just using a single machine to multiple machines, like a cluster. So it can handle really, really big data sets that are larger than the memory of a single machine, but the code itself looks really familiar, looks really similar to the code you'd write for like a single machine. So here's a really, really simple piece of code that I found on the internet that kind of demonstrates what I mean about the similarity, like the commands .read, .group by, the commands that were just mentioned in the previous presentation. So you can see that the commands are also really similar to the commands that you use in the Pandas data frame. But if we just go line by line and kind of see what's going on, the first two are the import statements, and it imports the Dask library and the Dask data frame module. And then the next line is reading the really large CSV. So if you were doing this on like a single machine, ideally this CSV would be super large that you can't even execute the computation because it takes up so much memory. But by having Dask, it allows you to read really, really large files. And unlike reading into a Pandas data frame, this operation is lazy, which means it doesn't use memory immediately, but it creates kind of like a graph to show when the task actually needs to be executed. And the Dask data frame as a whole is just honestly like a collection of smaller pandas that are kind of put together in a cluster when the computation is actually made. The next line is this line right here where you're actually performing the computations on the Dask data frame. And again, the group by, the category .mean are all, again, commands that we've already seen in the Pandas data frame, which it makes Dask really helpful in the first place. And then the last command is the command that's pretty unique to Dask. So like none of these operations actually go through unless you do the compute button. And the whole point of this is that it forces the lazy evaluation and it makes the Dask computation graph actually execute. So what usually happens is that this computation, if it's really, really big, is distributed among multiple machines, which kind of just upholds the whole point of a distributed operation. So the importance of Dask for distributed operations. So first, the scalability. Dask pretty much allows any user who has experience with NumPy or Pandas to scale their computations beyond the capabilities of just a single machine. So it's really, really suitable for big data processing, similar to the data that we'd probably work with in this research. It's also really good with resource utilization. So it is able to effectively use a lot of available resources in a cluster and help distribute tasks across workers to computers to maximize parallelism. And then ease of use, I think this is arguably one of the most important parts, is it provides a familiar interface for users who are already accustomed to libraries such as Pandas, NumPy, Matplotlib, etc., making it easy to transition from single machine to distributed computing. So like, for example, if you look here, we can see the similarities between the Dask data frame and the Pandas data frame. And honestly, if you just gloss at it and you look at it for like a second, it honestly looks like the same code, which is the whole point. Because you want it to be really easy to use and you want it to be so people who have experience with these other libraries can very easily transition into the Dask platform. So like for a NumPy extension into Dask, I'm pretty sure it's like an array. Yeah, arrays. Correct me if I'm wrong. But basically, the Dask provides like a Dask array, which is a larger than memory version of a NumPy array. So it's just a bunch of NumPy arrays in a Dask array. And then the same thing kind of happens with the Dask data frame. It's just a bunch of smaller pandas in a big kind of interface. And the main advantage of this is it operates on really large data sets by breaking them up into smaller pieces and then performing the operations through the lazy evaluation system. Another reason why this is important is because of flexibility. So Dask can be deployed on various computing environments, from a local machine to really big clusters. And this is important because it provides flexibility in infrastructure choices. And then lastly, it helps with optimized task scheduling. So the whole reason, the point behind the whole lazy evaluation thing is that you're able to choose which operations can be prioritized over others, which reduces unnecessary computation, helps conserve memory, and just overall improves performance. So that's all I have, because it's just pretty much an extension of what's been said before. But Arup, please add to my presentation because it's really high level.
Yeah, but I think you have done pretty well. The content you just shared is very good to all of you guys. To start something, and obviously you need to, like, whenever you write any piece of code or work in a project, obviously you need to read a lot of stuff. When you implement some things, you probably need to find or Google what part of the code base need a specific APIs. But this is a very good starting point. And one thing I want to tell you, like you said that workers, it's not workers, it is actually workers.
Oh, it
Because
is.
yeah,
Okay.
whenever even from the Cylon point of view and distributed or any other distributed computing point of view, ultimately the workers will perform different jobs,
Uh-huh.
and there will be multiple resources that will be allocated to the workers. So one worker can work in one CPU core,
Uh-huh.
and be one worker can take multiple CPU cores. It depends on the design, but yeah, worker is okay to tell. You can use worker.
Okay.
That's fine. And I have one questions. One question. So, do you have any references or any examples of performing any Dask operation on multiple node?
I don't have an example right now, but by the next meeting, I could try to get something working and like share at the beginning or after the presentation.
Perfect. So what you can do is, uh, take all the references and your reading materials and update the Excel file. You
Okay.
see that Google Excel file has a column, right? You can basically put all of your tutorial and references into the you know just I just create a column called references. So you can just paste all the references in the Excel file.
Okay, that sounds good.
Okay, so if you guys don't have any questions, we can move to the next segment, which is the Cylon paper. Let's go one by one. You'll get like at most 2 minutes to talk about Cylon paper. What you can do is just tell, like, what is this paper about, what are the technologies that are used in this paper, and what problem this paper is trying to solve. 2 minutes. Let's start with Aaron. Aaron, are you listening?
Yeah.
Okay.
The Cyclone paper. Just talking about like the.
Cylon paper.
Oh, sorry, Cylon paper. Yeah.
Mm-hmm.
It's just like a data model that's focusing on OLAP, which is online analytical processing, and it talked about how to use Apache Arrow and how it's more efficient for data structure and zero copy reads. And it also mentioned like a lot of operators, such as like it was like select, project, join, and union. And the two layers were the communication layer, which is and the transport layer. And it mostly just talked about how in a lot of like scalability tests in performance, like in comparisons against Spark and Dask, it was more efficient. And yeah, that's basically what I took from it. So
Yeah. Okay. Good. So let's go with Alex Fateh. Alex Fateh.
Yep.
Okay.
Yeah, so just not to repeat too much, I guess, on what he said. I think one of the major things was kind of a good overview of a lot of the different operators, like Aaron mentioned. So just a basic overview for the reader to understand. I think a little bit later, it dives more into the scalability specifically and the benchmarking versus the existing methods. So that's with the strong and weak scaling. I think that was an important point. And I think that was initially unclear to me. But I think that's a really important aspect. Just how different workers perform on different data sets. So having a lot of workers on some data sets may help, but on other data sets may slow things down. And then it also.
So yeah, sorry, Alex, to pause you.
Yep.
So you told you didn't understand the strong and weak scaling, or
I think last week, initially when we were first given the paper, I struggled to understand it, but I think it makes sense now to me.
Okay.
Yeah.
Yeah, probably on the all the people probably they don't know what is strong and weak scaling. Probably you, Alex, you or me, we can have a session regarding the strong and weak scaling. You are assigned to present MPI, right?
Yeah.
So could you please add some one or two slides regarding strong and weak
Yeah.
scaling? The we had a meeting last week probably, right? And
Yeah.
I told you how that things works. Okay, yeah, you can share all that stuff.
Yeah.
And this is very important. This strong and weak scaling is very important because whenever we perform any operations and try to measure the performance, we have to use different scaling technique. And strong and weak scaling are the two best techniques that are used in different papers. So yeah, go ahead, Alex.
Yeah. And then that was pretty much, I guess, like the biggest part that I mean, at least that I thought was really important. And then it continued with some related work. Talked about different language implementations with Java, Python, and C++.
Okay, so next is Alex.
Okay, I'm gonna share I made like a small slide. Can you see it?
Yeah, sure, Alex.
Okay, so honestly, there's a lot of repeat to what Alex already said, and but basically, Cylon's like a message passing interface, which couples with the current AI and ML data engineering data structures, and also can perform as a separate distributed framework to process and load data. So as Aaron mentioned, it falls under OLAP, online analytical processing, where it's bulk data processing, which is bulk reading and writing without much transactions. And some of the main operations that were also tested in the paper were select, project, join, union, intersect, and difference. Selecting certain rows based on their values or a subset of columns. Projecting is creating a simpler view of a table by dropping one or more columns. Joining, which is combining two tables based on a common column. Union, which is applied to two homogeneous tables to create a single table with the duplicates removed. Intersect, which is applied to two homogeneous tables in order to create a single table with only their similar rows. And then difference, which is applied to two homogeneous tables in order to produce only dissimilar rows. And then also mentioned by Aaron was the communication layer, which is using Open MPI or UCX to enhance Cylon's ability to run on multiple hardware devices. And then also the transport layer, which is also being able to communicate with any other transport layer that's also supported by OpenMPI, for example, TCP. And then in the test, in the graph, I have the paper pulled up here, but basically it's faster in Smart in both weak and strong scaling tests, and then faster in Dask and strong scaling tests for inner join. And that's pretty much it.
Yeah, thank you, Alex. You have covered a lot of stuff here. So next is I will skip Arup and go to Colin. Colin, are you hearing?
Yeah, so just not to repeat, what everyone was saying, but basically the problem at hand was, traditional data frame systems like R and Pandas had, performance limitations with really large data sets, and Cylon is a distributed and parallel data frame processing system made to sort of address that, right? And so it contains the distributed memory execution model, which basically sort of determines if operators need to be performed locally or in a distributed way. And like Aaron mentioned, they use the Apache Arrow to sort of format that physical data. And Alex just talked about the communication model and how it uses that open MPI to sort of use that P2P communication. And one of the conclusions from the tests was that lower latency in communication would be an area of improvement. And then its other model was the distributed operator model that focused on the local operators, like the single-threaded implementations, the auxiliary local operators, and the communication operators as well. It also talked about the cost models for various operations like shuffling, stuff like that, and not to repeat too much from the tests, but yeah, so that's what I got.
Yeah, thank you, Colin. So next is Lucas. Lucas, are you there?
Yeah. I'm sure we've pretty much covered most of it already, but just for my own take, I think something that was really important in the introduction of the paper was regarding like the communities that this work is important for, and how impactful Cylon can be for like enterprise research and just the research communities as a whole. As Colin said, data sets are very large, and we need to be more efficient as these data sets keep growing. And we need to get the most out of, like, we need resources beyond that of like a single node. And we have to be much more efficient with the data processing, like pre and post processing, which is why Cylon is, so important now, because as a distributed data like processing library, it integrates much better with things like PyTorch and as everyone has said, like Apache Spark, and just the utility of Cylon can make a pretty large impact on like the scientific community as like we work on integrating it with stuff like TensorFlow and PyTorch. And yeah, that's about what I have.
Cool. Okay, so Arup and Shia, if you guys want to add, you can. If you don't, it's totally fine. Because I told you guys not to focus on.
I feel like everything has been said already.
Mm-hmm. Yes, they basically shared almost everything. I want to add one or few points. The reason for this discussion is you guys get it right. See, the 8 people are talking about a single paper, and everyone is kind of sharing their own ideas. If someone added one point, other person finds some other stuff. So this is how, if we like read one paper together, like there will be a lot of different stuff that will come, we can discuss about that, we can learn from each other, right? And now you guessed it, like why we are here and why we formed this group. The main basic idea is we will go with the baselines of Cylon. We already and this Cylon is, this project is started at the end of 2019 and probably at the beginning of 2020. So and at the time there are a lot of different engineers out there, and most of the engineers they basically left. I basically involved in this project from 2021. And when they introduced Cylon, the primary focus is to develop a data frames that is faster than the existing one. So the reason for discussing this topic is after Orup's and Shreya's session. Orup's focus on Pandas data frame. Shreya's focus on Dask data frames. Now you see that Cylon has a data frames, and that data frames basically performs better than Pandas and Dask, right? And from here, we will expand the Cylon's capability. Okay, so the capability that can perform more stuff. So now there are a lot of different operations, for example, the distributed join, sort, intersections, unions, probably more than 40 plus operators. And our primary goal is to add more capabilities in terms of adding the features that can perform the job efficient, like all the hardware resources that will be used to perform the job. We should implement some features that can use those resources efficiently and perform the job, and get better throughput, right? And the second purpose will be we have to improve the frameworks of handling the data frames. So here we have used Apache Arrow, and there are still more places, or there is still some scopes to improve the query engines of Apache data frame, of Apache Arrow. And the third one is like add machine learning capabilities. So we do have capabilities of running machine learning training or inferencing job by using PyTorch or TensorFlow, right? But those frameworks needs data, a very efficient data frames for their processing. And there was a survey conducted by Anaconda that near about 45% of the developer time in industry or research institutes take pre-processing of data. Then that data will go through the models and probably perform training and inferencing. So we need efficient data frames, and as well as we need efficient mechanism to perform machine learning job, so that we can give the model better resource and also better output. So that is the third part. And the fourth part will be optimizing the compiler level. There will be, if we talk about TensorFlow or PyTorch, whenever we create any data frame or any tensors for machine learning, let's say, those tensor has to go through a series of interpretations underlying to the underlying the PyTorch frameworks, and it interpret into multi-level of output queries, and that then finally go to the LLVM compiler and then translate it into the hardware language or machine language. So we do have some scopes to improve the query engines. We will not go in detail of the compiler level, rather than work on top of that, probably optimize some stuff of handling Arrow. Arrow has a query engine, so the primary job will be optimize Arrow query engine. So that's one part of the projects. And the fifth one is basically given infrastructures to execute heterogeneous tasks. That project I am currently working on, and I have a proposal. I already present my proposal, and and I'm working on it, and this is working in progress. But there is still a lot of places that we can, we can improve. And think about that. I probably told you that when when we had a discussion for the very first time regarding how Chat GPT or Google Bard works, right? They have a very strong infrastructure stack and that can handle multiple tasks at the same times. But those systems are basically closed source. So here we are trying to build something that will be open source for the research community, and and we will try to give a heterogeneous execution environment for machine learning, for data engineering, or any other kind of task. So if you guys are, and if you guys continue with us for like another semester or for probably more, this project will continue for more than 1 or 2 years. Even I'm not, even after my graduation, someone will be here, or probably one of you guys, if you are interested to work in these projects. So this from the exposure point of view, this project will give you a very good exposure to the latest technologies of high performance computing domain. So yeah, that's all from my side. If you guys have any questions. Okay, so can anyone tell me when is the next class? When you guys are coming back from your hometown? Are you going to your hometown for Thanksgiving?
Yeah, I'll be back the Monday after Thanksgiving.
Monday,
Yes.
next Monday. Okay,
Same.
Monday.
Yeah.
So what I would suggest, I will not give you any anything to present on Tuesday. Probably on Tuesday, Asad will present process and thread. That's fine. So what I will do is I will try to take a session after Asad about the building process of Cylon. Okay. So what you need to do is, clone the Cylon projects into the CS cluster. Okay. That's it before Tuesday's session. And I will prepare a document. We will go together like at the same time. So it will be on-job training. On-job training, it means I will do the stuff at the same time you guys will do, so that we can fix the problem. We can basically ready our environment at the same time. So if we have problems, other can help. Did you get my point? Cool. So yeah, do you know the GitHub repository of Cylon? Do you guys check that? I have shared. Who doesn't know? Okay, anyway, let me, it's fine if you don't know, let me share the GitHub repository of Cylon. So this is the GitHub repository of Cylon project. So you run it, keep it into the CS cluster. So this is very important. If you don't have access to the CS cluster, please let me know, because in today's session we will have a on-job training. How the Cylon, we can build Cylon, and as well as the code, the basic code structure of the Cylon project. Okay. So, any questions?
Yeah, I just got a quick one. So
Mhm.
all we need to do is just make sure that we have access to that CS cluster.
Access to the CS cluster, and after accessing it, you need to clone that project.
Okay, thank you.
Yeah. Use the Git, and then obviously clone the projects into your home or any places you want. Okay, so no other questions? Perfect. So thank you guys for joining this call, and yeah, see you on next Tuesday.
Thank you.
Bye.
Thank you.
Thank
Thank
you.
you.
Thank you.